x of k and summation n is equal to 0 to n minus 1 x of n w power nx nk and capital N. So let me explain all these terms. So where capital X defines the frequency domain representation, and k represents about frequency coefficients, and small x of n tells that it is in a discrete time. So where small x, it tells about representation of time in time signal, and n is the number of time indexing discrete samples. Okay, so coming to the w means it is in a twiddle factor. We have to, what is this w? So let me write this capital W. N capital N is nothing but e power minus j 2 pi n k divided by capital N. So the formula for this twiddle factor is e power minus j 2 pi by n n k, right? So all the time writing this complex term is difficult. So that's why we have considered this one as a twiddle factor. So from this twiddle factor is nothing but w is represented as e power minus 2 pi 2 pi, right? So when we write completely, then we can get this formula. Okay, so if you expand this formula, so with an expansion n is equal to 0 to n minus 1 summation, when you substitute n values in each one, we are going to get n is equal to 0, w0k suffix n. Next term is x1 w1 nk suffix capital N. Like that, we will prolong up to n minus 1 terms. So this is the expansion of the above formula. So that means x of k will be having this expansion. So if you see this expansion, we can see this w term is in a complex term, and this is in a time some real value, and we can identify this the operation between x of n and w of nk is in a multiplication, and this multiplication, and here also multiplication, and here also multiplication, right? And how many additions are there? So this whole total term, after multiplying, we are going to get some complex value that will be added to second term, and that will be added to third term, like that. We are going to have n 0 to n minus 1 terms. So from this we can see that how many multiplications are there, how many additions are there. For example, if we further expand for k value is equal to 0, so this is for an expansion, and this by substituting in this above formula, k is equal to 0, we can get this expansion. See this? So earlier, if we place k is equal to 0, here it becomes 0. In the place of n, if you place 1 into k, that means k0, this is the term, and like that. So finally we are going to get this one. So this equation tells that for k is equal to 0 frequency component, what will be the expansion of this DFT. Similarly, we are going to have for x of k is equal to 1 and k is equal to 2, and x is equal to k is equal to 1 and k is equal to 2, and for k is equal to n minus 1. So from this we can tell how many multiplications are required and how many additions are required. If you consider for one this equation for k is equal to 0, for k is equal to 0, how many additions are required? One addition, so another addition, and another addition, like this. So that means we are going to have n minus 1 additions. So that means n minus 1 additions are required. And if you consider for multiplications, multiplications. So this is addition, and n multiplications are required. N multiplications are required. So how that we can understand? So this is one multiplication, this is one multiplication, this is one another multiplication, like that 0 to n minus 1. That means n multiplications. So for additions, 0 between two, no, this so this one, this component and this component, and like that up to end this one. So we have n minus 1 additions. So this is what about the computation, direct computation. What we can conclude from this direct computation, if you want to compute a DFT directly, so the number of complex multiplications required are n, and number of complex additions required are n minus 1, right? So this is for one equation. If that number is for k is equal to n values, so 0 to n minus values, that will be multiplied into n, right? So that we are going to discuss in the next slide. Why we are using this complex term here? Because all the here the multiplication x of 0 with w n0, this is a complex term. That's why we call this one as a complex multiplication. And the product we are going to get is complex number. Again, this one is a complex number with x of n. We are going to get complex number. This complex number and this complex number both are added. So that's why we call that one as a complex multiplication, complex addition, right?